All right, and so I'm going to go ahead and download this Lewis structure. I do have I think a copy on my tablet, but I forgot to erase all of my work. So just give me a second here. I just need to airdrop this to my tablet.
Off topic really quick, Sam, if you want to possibly after the semester try gaming together or something, says I believe you said you're a gamer, correct? You can.
Yeah, I only have a laptop, but I still have a Steam account and everything.
Sounds good. We should trade information then.
Yes.
What are you guys gonna play?
No idea.
No idea. Do you have a PS4 by chance or PS5?
No, I'll probably stay away from the newer consoles for a while, just because I don't see the cost benefit in those right now.
Well, I got an Oculus Quest 2 for the Beat Saber, and
Nice.
it's awesome.
Importing. All right, cool. Sorry, it's taking some time for to transfer. I don't know why. All right, and so today it's all about Lewis structures. If you guys had me for lecture, we already went the rules. For those who don't have me for lecture, I'm hoping that your lecture professor has gone over specific rules on how to solve or draw these Lewis structures. And so this is not a guessing game. There is a specific step. There's specific procedures on how you guys should be able to successfully draw Lewis structures. And it does involve calculating formal charges for elements, for central atoms that are not fluorine, oxygen, nitrogen, and carbon. And so the first page that you guys are seeing here, this is just an example of what we will be doing. So we're going to go ahead and count the total number of electrons, determine the central atom, draw a draft, make sure that the hydrogens follow the duet rule. The central atom follows the octet rule if it's FONC. If it's not part of func, fluorine, oxygen, nitrogen, carbon, then we have to calculate its formal charge to determine whether or not it's whether or not we need double bonds or triple bonds. And then after that, we're going to do a 3D sketch. We're going to describe the electron geometry, the molecular geometry. Let's go ahead and identify bond angles, and then we're going to go ahead and work with the molecular model picture. And so this is a Word document. And so if you guys wanted to, you guys can take a picture of these molecular models and then somehow drag it into at the very end of the Word document. I think it's kind of tough dragging it right in the middle because it might distort all of the formats for the rest of the pages. And so you guys have a couple options in terms of submission. You guys can do 2 submissions. The first submission can just be this document that has all of this information. And then the second document in your submission can be your pictures. When you guys are submitting your pictures, if it's a separate document from the main document, just please make sure to identify what molecular substance you guys are working with. And so you guys should have your molecular models with you in your lab kit. And this is the last item that we're going to do for today's lab. And so one other thing, if this video is getting passed around to other students who are not in my lab, I did remove some other assignments. So you guys are only going to be focused on this assignment. I believe there was supposed to be another assignment, or there's something else. I can't remember if it's like a group discussion or something like that. I'm not going to assign that. You guys have way too much on your plate. And so let's just keep things simple and just, work on this worksheet, and then we're done. All right. And so the first thing that we're going to do is water. So we have H2O. When you guys are first drawing Lewis structures, you guys need to determine the total number of electrons and the central atom. And so the total number of electrons for water, and we did this in lecture, I believe. I'm not too sure for those who don't have me in lecture, whether or not you guys did water in lecture. But to determine the number of electrons, you're looking at group number for each element. And so we have hydrogen and we have oxygen. The group number for hydrogen is 1, and then there's 2 hydrogen. So we're going to go ahead and multiply that by 2. And then the group number for oxygen on the periodic table is located where? What group?
Group 6.
Yep, you got it right. So group 6. And so since there's only 1 oxygen in this chemical formula, just multiply it by 1. And you guys get 6. And so the total value that we get here is 8. So there are 8 valence electrons that we're going to have to place around this molecule. And so, I'm sorry, we're going to have to place 8 valence electrons throughout this molecule. And so when it comes to the central atom, hydrogen is never the central atom. It is always a surrounding or a peripheral atom. So we only have one option in this case. It's just going to be oxygen. And so since the central atom is oxygen, when we're drawing the Lewis dot structure, we're just going to go ahead and put oxygen right in the middle. And then we're going to go ahead and put, hydrogen, and we're going to surround it with a hydrogen. And you guys can, orient these hydrogens any which way, simply because this is a 2-dimensional depiction of this molecule. When we're talking about the 3D sketch a little bit later on, we're going to go ahead and use bold, or I'm sorry, I keep on saying bold, I'm used to saying bold, but it's officially called wedged. We're going to use wedged and dashed lines to represent the 3-dimensional character for this molecule. And so since we have 8 valence electrons to place, the first thing that we need to do when you guys are drawing these Lewis structures is we're going to work outside and then work inside, right? So that's a general process. So we have to make sure that the surrounding atoms have the full valence shell. For hydrogen, hydrogen follows a duet rule. So by putting 2 electrons between oxygen and hydrogen, it fulfills the valence shell for hydrogen. Okay. And so here, hydrogen technically owns 1 electron, and it's sharing 1 electron between oxygen and hydrogen. Okay, and so we've used 2 out of the 8. And so we have 6 remaining. We're going to go ahead and put another set of 2 electrons between this hydrogen and this oxygen. And so once you have fulfilled the valence shell for the surrounding atom, you guys are going to go ahead and subtract that from your total. Insofar, we used 4 valence electrons. And so we have 4 valence electrons remaining. And so anything that remains is going to go on the central atom as a lone pair. So remember that a lone pair requires 2 valence electrons. So I'm just going to go ahead and represent the 4 valence electrons in a different color. So that's 1, 2, 3, 4. So this is the Lewis dot structure for H2O. If we wanted to convert the Lewis dot structure into a Lewis structure, in other words, we're representing shared electrons as a line, then this would be a single bond because there's just 1 pair. This is a single bond because this is just 1 pair between oxygen and hydrogen. And so what we have here is something that looks like this, if we're trying to represent it in terms of just a general Lewis structure with lines between 2 atoms. Does that make sense?
Yeah,
Okay. I know that we did this in class, and so hopefully this feels a little familiar. And so we're going to go ahead and talk about the electron geometry and molecular geometry. So once again, the electron geometry, or EG, and for those who have me for lecture, feel free to take that out. There's also a reference chart. I think that reference chart, did I put the lab in here? No. Let me see. So this is in your Chem100 canvas. When you guys are trying to use this specific reference to determine the electron geometry, molecular geometry, let me see here. Actually, let me go ahead and rate. Well, no, I'm not gonna erase it. So just imagine that this sheet is blank. When you guys print this page, or when you guys are using this page, I need you guys to put a line where you guys see the pink highlight. Okay, and so anything to the left of this pink highlight is referring to the electron geometry. And so when we're trying to identify the electron geometry, we're trying to determine how many groups of electrons surrounds the central atom. And when we're trying to determine molecular geometry, we're going to distinguish of the number of groups of electrons, how many of them are actually bonding, how many of them are actually lone pairs. And so that's the main distinction between electron and molecular geometry. Molecular geometry is describing the shape of the molecule based on actual bonds formed instead of bonds and lone pairs. So electron geometry is focused on describing the shape of the molecule based on bonds and lone pairs. Molecular geometry only takes into consideration electrons that are bonding. Okay. All right. So for this semester, you guys were only focused on 3. And so this worksheet, so I want you guys to go ahead and take a highlighter or whatever, and then put a line through between 4 and 5. And so we're only going to be focused on the first 3 shapes. For those who are moving on to Chem110, if you guys download this in your Canvas shelf from Chem100 lab, not from my lecture, 5 and 6 is going to be for Chem110. So you guys are going to talk about trigonal bipyramidal. You're also going to talk about octahedral. And so these are the different variations depending on the combination of bonds and lone pairs. Okay. And so looking at H2O, I'll go ahead and write it here real quickly. So this is the Lewis structure for H2O. If we're talking about if we're talking about electron geometry, we need to describe groups of electrons. And so when you guys are identifying groups of electrons surrounding the central atom, this is a group of electron, that's 1. This is another one, that's 2. This is another one, that's 3. This is another one, that's 4. So we have 4 groups of electrons surrounding oxygen. Notice how I do not care about the identity of the surrounding element. We're only focused on the electrons surrounding oxygen. And so because we have 1, 2, 3, 4, this is going to be tetrahedral. The electron geometry is tetrahedral, and the bond angle is going to be 109.5. Now, if we're trying to identify the molecular geometry, so we know that we're tetrahedral. So for the molecular geometry, it's one of these 3, okay? And so of the 4 groups, 1, 2, 3, 4, how many are actual bonds and how many are lone pairs?
2 bonds, 2 lone pairs.
Okay, 1, 2, and then 1, 2. So that combination is here. So that's 2 bonds and 2 lone pairs. So the molecular geometry is bent. And so this is the overall shape of something that's bent. And so we're just going to go ahead and write that down. And then the bond angle for anything, let's see here. I don't think this page has it. And so if, let's see here, since the bond angle for tetrahedral is 109.5, the moment that you guys have lone pairs present, then the bond angle is going to be less than the theoretical, which is less than 109.5, less than 109.5. Okay, so that's going to be the bond angle for anything that is going to be less than ideal. Or I'm sorry, that's going to be bond angle for the 2 molecular geometry structures that's not tetrahedral, but still falls under the tetrahedral family for electron geometry. Okay. All right. And so notice how I have like 3 copies of the same worksheet. Did we do this one? Nope. That was, is it this one? Nope. Are we on this one? Yep. Sorry. All right. So the electron geometry for water is going to be tetrahedral. And then the molecular geometry is going to be bent. Okay. Now the bond angle for tetrahedral is 109.5. And then the bond angle for a bent structure is less than 109.5 under the tetrahedral family. Okay. All right. And so when we're trying to depict this in 3-dimension, we're going to identify that bond angle. And so once again, I am going to skip the 3D sketch and the molecular model picture for now. I want to go through these steps very quickly, and then we're going to go back and we're going to look at a simulation as well as our molecular model kits to develop the 3D sketch. And that way you guys can also take a picture of your molecular model. All right, so the next one here is methane. So here we have CH4. Talk me through this. So here we have carbon, hydrogen. How many carbons, how many hydrogen, what's their group number, etc.
1 carbon, 4 hydrogens, and I think carbon's in group 4.
Correct.
I recall. And hydrogen group 1.
Yep. Okay. And so here 4, we have a total of 8. All right. And so what's the central atom?
Carbon.
Good. All right. So that's done. So central atom is carbon. We're going to surround it with hydrogens. So what's my next step?
To do it.
Okay. So since our surrounding atom is hydrogen, we're going to go ahead and put in 2 electrons max between carbon and hydrogen. So 2, 4, 6, 8. Okay. All right. And so to connect all of the atoms, all the hydrogen atoms to carbon, we had to use up the total or the maximum number of valence electrons that we calculated. And so here we have 8 valence electrons minus 8 valence electrons used. So this calculation tells us that there is no lone pairs. And so I've taught this enough times to constantly see this, but this calculation, a lot of students take it for granted. The moment that it says 0 lone pairs, in your final draft, there should be no lone pairs on your central atom, right? And so here in the previous calculation, we see that there's 4 valence electrons, in other words, 2 lone pairs. And so if there's 2 lone pairs in your central atom, then you must have 2 lone pairs in your central atom at the very, very end. And so sometimes I see students, do weird things, and then they create double bonds and triple bonds that is not supposed to happen, and it's not reflected in their initial calculation. So just, some things to keep in mind. And, I get it. It's close to the end of the semester. So there's just a lot of things going on. And it's unfortunate that this topic is actually covered closer to the end rather than the beginning, where you guys can have more time to practice. All right, so that's pretty much it. If I wanted to translate this Lewis dot structure into just a general Lewis structure that shows bonds, I have 1 pair here between these 2 atoms, so that's just a single bond. Okay, so the pattern repeats itself all throughout, and this is basically my structure. Okay, so what is my electron geometry?
Tetrahedral.
Okay, very good. So I have 1, 2, 3, 4 groups of electrons, right? 1, 2, 3, 4 groups of electrons. So it's tetrahedral. Bond angle for tetrahedral?
109.5.
Okay, very good. What's the molecular geometry? So out of all of these surrounding electrons, how many of them are bonding? How many of them are not bonding? And what's the shape? What's the bond angle?
Tetrahedral, 109.5. 4 bonds, 4 lone pairs.
Yep, very good. So it's tetrahedral. Here we have 4 bonds. Okay, 0 lone pairs. So I'm going to abbreviate lone pairs as LP. And so that would be the combination that we're looking for in our chart. And then here, they're just 4 groups of electrons. All right, so that's CH4. So we're going to go ahead and move on to CO2. Okay, and so total number of electrons, same deal, guys. I have carbon and oxygen. How many of each? What is their group number?
One carbon, 2 oxygen. Carbon is group 4, oxygen is group 6.
Awesome. And so 1 times 4 is 4, 2 times 6 is 12. So you get a total of 16. So there are 16 valence electrons that we're going to have to place in our Lewis dot structure. And so this is our first encounter in this worksheet, in which we have 2 atoms that we have to consider in terms of it being the central atom. So we have carbon and we have oxygen. So the previous 2 examples, we had hydrogen. So the hydrogen was automatically eliminated and we only had 1 atom left. But here there is no hydrogen. And so we have to determine which of these 2 atoms is considered the surrounding atom. And so I'm going to go ahead and quickly go to my lecture, because it has all of the stuff that I want. And so I apologize for those who don't have me for a lecture, but you guys can go ahead and take a screenshot. And so when you guys are determining the central atom, you guys can do this one of 2 ways. If we're talking about metallic character, you want the element that is most metallic. So between carbon and oxygen, here's carbon, here's oxygen. We're increasing the metallic character from right to left. So according to this, carbon is more metallic than oxygen. So therefore, carbon is our central atom. If you guys were taught electronegativity, it's going to be the least electronegative. So carbon is, its electronegativity value is about 2.5. Oxygen is 3.5. So carbon has a smaller electronegativity value. So therefore, it is the it's going to be the central atom. Okay. Does anybody need a screenshot of this? It's not in your, for those who don't have me for lecture, or even for those who have me for lecture, I'll give you guys a chance to screenshot this just in case. We're good? Cookies. All right, and so let's go ahead and go back. All right. So now that we determined that carbon is our central atom because it's the most metallic and least electronegative. So most metallic, least electronegative. We're going to go ahead and do the draw the Lewis dot structure. So we have carbon in the middle, and then we're going to surround it with oxygen. Okay. And so since we're not dealing with hydrogen, how many electrons do we have to place on each oxygen?
8.
8. And so we're going to go ahead and put in 2. Let me move the oxygen just a little slightly closer here. So we're going to put in 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And so I've filled the valence shell for oxygen. I have an octet. I have an octet. And so according to my calculation, I have to place 16 valence electrons. And then I've used 16 valence electrons. So 8 plus 8 is 16. And so this calculation lets me know that I have 0 lone pairs. And so if I have 0 lone pairs in my calculation, my final structure, the central atom, will not have any lone pairs. So no lone pairs on central atom. Okay. And so with this third piece of information, it'll help us kind of finalize this Lewis dot structure. And so if we're looking at the surrounding atoms, we have the octet. Here we have the octet, so we're good to go. If we're looking at the central atom, carbon, carbon has 1, 2, 3, 4 electrons surrounding it. And so remember that 4 elements, F, O, and C, func, fluorine, oxygen, nitrogen, carbon, if they are your central atom, then it must follow the octet. Okay, no questions asked. Now, there's no other, how do I say this? Since there's only 4 electrons surrounding this carbon, where this carbon is not happy, it doesn't have the octet. And so when you guys fall upon this situation, what you want to do is you want to create double bonds and triple bonds. And so one way that you guys can, actually, it's not so much one, the only way that you guys can form double bonds and triple bonds is to take a lone pair from a surrounding atom that has a lone pair, and you're going to transfer it between the 2 atoms. And so notice how this, I didn't take this lone pair and transfer it, so far, I didn't transfer it to the other oxygen. It has to, this lone pair has to stay between the original owner of the lone pair and the central atom. Okay. And so if you kind of draw a circle around this, I have 1, 2, 3, 4, 5, 6. So I'm almost there. Okay. Now you might ask yourself, okay, well, wouldn't I get 8 if I were to take this lone pair and transfer it to carbon? Yes, you would. So if you were to take this lone pair and if you were to circle around it, or if you kind of circle around it, you have 1, 2, 3, 4, 5, 6, 7, 8. But there is a general rule that you want to try to form as much double bonds first, and only when all options of creating double bonds are exhausted. And if you still are not fulfilling the octet rule or the formal charge rule, then you can form triple bonds. And so what I'm trying to say is that there is another source of lone pair on this oxygen. And so to create the 8 valence electrons for carbon, we're going to take a lone pair from oxygen and place it between this carbon and oxygen. And so we can still create another double bond versus creating a triple bond. Okay. And so if you have another source to create a double bond, that is much more favorable than creating a single bond and a triple bond. There's only a few instances in which a triple bond will actually be formed, and it's a very niche scenario to the point where you're kind of cornered to form a triple bond because there's no other lone pairs to create double bonds right, without breaking octet or something like that. Okay, I don't know if that was confusing. Does that make sense?
Yeah.
Okay. And so anyways, if you put a circle around carbon, you'll notice that you have that carbon has 1, 2, 3, 4, 5, 6, 7, 8. And remember that there's no lone pairs on carbon. And so, I mean, we fulfill just that. We don't have any lone pairs on the central atom, which is carbon. And so this is the Lewis dot structure. Also, we can go ahead and check oxygen to see if we broke its octet. 1, 2, 3, 4, 5, 6, 7, 8. We did not break its octet. So same thing here. These 4 are shared between oxygen and carbon, so you can double count it. And so if we're trying to draw the Lewis structure, if you have 2 pairs of electrons like this, that translates to a double bond. Okay. All right. And so lots of things coming out of my math today. Lewis dot structures is just one of those things. Anyways, electron geometry. So we're focused on groups of electrons. How many?
4.
Okay. Don't take offense to this, but the answer is no. And so when it comes to double bonds,
2, right?
exactly. All right. So if you have a lone pair, that's one group. Actually, let me. So if you guys have a lone pair, that's one group. If you guys have a single bond, that's one group. If you guys have a double bond, that's one group. If you guys have a triple bond, that's one group. So anything that surrounds the central atom, it's counted as one. So this is a double bond. So that's one group of electron. This is another double bond. So that's another group of electron. So really what we have is 1, 2 groups of electrons. And so if you have 2 groups of electrons, what is the electron geometry?
Linear.
Bond angle?
180.
180. So what about the molecular geometry?
Would it be the same?
It would be the same. So of the 2 groups of electrons, 2 of them are bonding and 0 lone pairs. Okay, so that combination would give us linear, and bond angle is 180. So I know that I'm not going back and forth between the chart. And so if you guys have the molecular geometry, chart with you. It's basically right here, right? And okay. All right, and so if you're able to work off of 2 screens, just make sure you guys have that reference on hand so you guys know where I'm getting these answers from. All right, so we're gonna skip that. Next is BF3. Okay, so let's go ahead and go through it. We have boron and fluorine.
Can you go back really quick? I'm sorry.
Yeah, you're fine.
Because how is there not any lone pairs? I know we have the 2 double bonds, but aren't the lone pairs above the 2 oxygens count?
Everything is with respect to the central atom.
Okay, so it's just no lone pairs on the central atom determines the geometry?
Yep, yep. And so when you're talking about electron and molecular geometry, you're only focused on the central atom and what it's surrounded by. You don't care about the identity of the surrounding atoms. And you don't care about the lone pair. So nothing about nothing about the surrounding atoms applies when you're talking about electron geometry and molecular geometry. You're simply focused on the central atom and what's directly coming out of the central atom, whether it's lone pairs, double bonds, triple bonds, single bonds. All right, and so let's go ahead and do BF3. So we have 1 boron, 3 fluorines, group number for boron, group number for fluorine.
3 for boron. 7 fluorine.
Yep. So 3, 21. We have a total of 24 valence electrons. So between boron and fluorine, which is essential?
Boron.
Why would that be?
Because it's the least, was it metallic, or what was the term?
Oh, least electronegative.
Yeah.
Yep. And so if you're talking about metallic character, boron is further to the left. So if you guys are looking at the periodic table, boron is in the 3rd group, and fluorine is on the 7th group. And so boron is the most metallic and least electronegative. So most metallic, least electronegative. So we're going to put boron right in the middle. We're going to surround it with fluorine. And so our first step is to place electrons around our surrounding atom. And so since we're not dealing with hydrogen, then how many electrons do we place around the fluorines?
8 for each.
8 for each, correct. Right. And so if it's not a hydrogen, default to 8. So here I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, cool. So 8 times 3. So here we placed 8. The pattern is 3. We repeated it 3 times. So 24 minus 24 is 0. So there is 0 lone pairs on the central atom. Okay. So our final structure should not have a lone pair. And so when you guys are looking at BF3, we notice that the fluorines have the octet. That's cool. If you guys are looking at boron, notice that we have 1, 2, 3, 4, 5, 6. And so boron does not have the octet. But since the central atom is boron, boron and beryllium are 2 elements in the 2nd period that does not have to fulfill the octet rule. So boron is happy when it has 6 valence electrons surrounding it. Beryllium is happy when it has 4 valence electrons surrounding it. And so since we have, 1, 2, 3, 4, 5, 6 surrounding boron, this actually fulfills its valence shell. Excuse me. It has to do something with hybrid orbital, with electron configuration and SPDs and its stability. And so don't worry about the reason why. Just remember that boron has, if you guys hit 6, then it's happy. For beryllium, if it's a central atom, then it's 4 and it's happy as well. Okay.
So we do not need to move any away from fluorine?
Correct. And so since there's 6 surrounding boron, this is the final structure, right? And so if you want to translate this as a Lewis line drawing, this is boron, fluorine, 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 and 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Okay. All right, cool. And so what's my electron geometry? How many groups of electrons surrounds the central atom?
3.
1, 2, 3. And so there's 3 groups. So what does that mean in terms of the shape and bond angle?
Trigonal planar 120.
So here we have trigonal planar, and the bond angle is 120. Okay. And so you guys are going to be using the reference chart that's provided in the Canvas shell to determine this. So molecular geometry, what's my combination? Bonds and lone pairs.
3 then 0.
So here we have 3 bonds, 1, 2, 3, and 0 lone pairs, because there's no lone pairs on the central atom. So 3 bonds, 0 lone pairs, and what would be the molecular geometry?
The same.
Yep, it would definitely be the same. All right, cool. So we're done with number 4. I think there's like 12. Anyways, so let's go ahead and do the next one, CLF3. CLF3. So here we have 1 chlorine, 3 fluorines. What's their group number?
Both in group 7.
Good. And so 7 and 21, total of 28 valence electrons. What's the central atom?
Fluorine.
For what reason?
It's the least electronegative.
Good. So least electronegative. So you just need one justification. You don't need both. If you guys are going through electronegativity, then that's okay. And so we know that if you look at our electronegativity table, chlorine, actually fluorine is the most electronegative. So anything outside of fluorine is going to be the least. So with that said, we're going to do chlorine right in the middle, and then we're going to surround it with 3 fluorines. Okay. Since we're dealing with an atom that's not hydrogen, we're going to go ahead and make sure that the surrounding atom has the octet. Okay. And so I am using let me scoot this further in. So I am using a total of 24, right? So 8 times 3 is 24. Let's see here. So 28 valence electrons minus 24 valence electrons. And that would give me 4 valence electrons remaining. And so this is a number of non-bonding electrons. And so what does this mean in terms of the central atom? What do I do with
2 lone pairs?
correct? So that means that there's 2 lone pairs on central.
Wait, why 2?
So lone pairs has 2 electrons.
Right?
And so how many pairs can you make with 4?
Okay.
I
That
don't know if
makes sense. Okay, sorry. I was looking at the central atom and thinking 3 because of the 3 pairs around chlorine. My bad.
Oh, I see. This is known as a bonding electron because it's between 2 elements. So this is this right here is a bonding electron. It's between 2 elements. And so these would not count as lone pairs. So we would have to actually add lone pairs to the central atom. Oh, it's interesting that I think this worksheet is different from previous semesters because now you guys are working with higher geometries. You guys should not be working with higher geometries until 110. Interesting. I wonder why they changed that. Anyways, so I know it kind of looks a little off right now, but I kind of color coded it differently. So notice how this electron is not, if you look across, there's no element. So this is a lone pair. This electron is by itself. There's nothing attached to it. So that's a lone pair. Okay. So I'll go ahead and kind of highlight, I'll highlight the 2 lone pairs as pink, just as a physical reminder. Interesting. All right. And so let's go ahead and check our draft. Fluorine has 8, fluorine has 8, fluorine has 8, fluorine is happy. Let's go ahead and check our chlorine. So when we check our chlorine, it's all of the electrons that's directly surrounding chlorine. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is the first instant in this worksheet where we have 10 electrons surrounding the central atom. Usually it's 8. And so that might ring an alarm in your head, like we're not following the octet rule. And so I'm not too sure if your lecture professor covered this, but basically the octet rule for your central atom. So if your central atom is part of func, so fluorine, oxygen, nitrogen, chlorine, or sorry, carbon, they must follow the octet. So that means that if your central atom is any element outside these 4, to check your work, you need to calculate formal charges. And so the central atom is not part of func. And so because our central atom is chlorine, then we need to calculate formal charges to confirm whether or not we have a double bond or triple bond that's required for us to create. And so the formula for formal charges is pretty simple, I think. So it's basically the number of, actually, let me take a step back. So the original number of valence electrons for that central atom minus number of bonds minus number of non-bonding electrons. And so the central atom is chlorine, so chlorine is in question. So to calculate formal charge for this central atom to confirm whether or not we need a double bond or a triple bond, we need to go through this process. So the original number of valence electrons for chlorine is 7, because it's group 7. And so how many of these electrons that I'm circling are actually bonds?
3.
Correct. So 1, 2, 3. So we have 3 bonds. How many of these electrons are non-bonding?
2.
So you're somewhat correct. So there's 2 lone pairs. It's the one in pink, but notice that this formula is not asking for lone pairs. It's asking how many electrons are not bonding.
So 4.
4, exactly. So the non-bonding electrons is actually the calculation from the subtraction. Okay, and so this is going to be 4, not 2. So if you subtract this, 7 minus 3 minus 4, that's actually equal to 0. And so when you have a formal charge of 0 for your central atom, that means that there's no double bonds or triple bonds that needs to be formed. Okay. And so with elements outside of FUNC, FONC, the only way that you guys will know whether or not to create double bonds or triple bonds is through formal charges. If your central atom is FONC, if you don't have the octet, then you create double bonds or triple bonds to get the octet. Okay. And so hopefully that, I'm not too sure if you guys will remember that. I mean, with more practice and all of that stuff, hopefully you guys can or will remember it. I think there's some more examples in this worksheet that will exercise the use of formal charges and when to use it.
Weird question. If we weren't taught this from our lecture teacher, is it still relevant?
It's highly relevant.
Okay, 'cause she did not touch on this at all.
Oh, I know.
About formal charge.
I definitely know that. And so there's very few instructors for Chem100 that actually teaches formal charges, and it needs to be taught. The reason why is because students who draw, for example, sulfate or phosphate, they don't, it's not a complete Lewis structure because they don't have the double bonds. And so you guys will need to know this for Chem110. And so this is a powerful tool to help you develop the correct answer. And so we'll go through some more examples. Okay. Now, I'm thinking that if your instructor didn't teach you formal charges, then I'm hoping that the molecules that you guys get on your exams just involve these elements as your central atom, so that way you don't have to think about formal charges and you'll just move lone pairs from the surrounding atoms to create your double bonds and triple bonds based on octet rule. Okay. All right, but it looks like this worksheet is asking you to do some 110 stuff. All right, so anyways, let's go ahead and talk about electron geometry. How many groups of electrons do we have surrounding the central?
5.
4 or no, 5, right?
Correct. 5. So I apologize. Let me go ahead and just translate this very quickly to just a general Lewis structure. So that way we can see it much better. And then I'll do this in pink, 1 and 2. Okay. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, just so that way you guys can see it. if we go back to the molecular geometry, if we have 5 groups of electrons, we're actually in trigonal bipyramidal. So trigonal bipyramidal, the general shape looks like this. It's like a pyramid, but there's 2 of them. Okay, so this is the general shape of trigonal bipyramidal. There's 2 pyramids, that's why it's called bi. And it's trigonal because there's 3 phases, 1, 2, 3. So 1, 2, and then at the very back, there's the 3rd face. And so they definitely did change this worksheet from spring semester, because we didn't go through higher levels than tetrahedral. Oh well, it is what it is. And so electron geometry is going to be, so there's 5 groups, just like what you said. And that is trigonal bipyramidal. Now the bond angle, there's actually 2, 120 and 90. Okay, and so I'll go ahead and show you where the 120 is. And so with trigonal bipyramidal, you guys have items. Let me go ahead and just, okay. So this is the general structure of trigonal bipyramidal. Notice that here we have a line going here, we have a line going here, we have another line going here, we have another line going here. And so these 3 points that forms the horizontal triangular platform for the trigonal bipyramidal shape, these are known as equatorial. And so anything that goes up and down is called axial. So if you're looking at this angle, axial to equatorial, that's 90 degrees. Okay, so let me put that here. So this is 90 degrees. If you're looking at equatorial, so we're looking at this bond, that's 120. Okay. It's kind of hard to see it in 2 dimension. And so when we go back and look at it through a simulation, we'll be able to see the 120. So basically, if your eye is at the very top of the structure, and if you look down, what you see is something that looks like this. So this bond angle is 120. It's like trigonal planar, but flat. Okay. And so I'll go ahead and we'll explore the bond angles when we do the simulation stuff. So in terms of the electron geometry, I'm sorry, the molecular geometry, of the 5 groups, how does that break down to bonds and lone pairs?
That would be 3 bonds and 2 lone pairs.
Yep. Yep. So 1, 2, 3 bonds and 2 lone pairs. Okay. And so it doesn't matter if you guys have me for lecture or it looks like you guys do need this for you guys do need this worksheet for this lab, because I didn't cover this for lecture. All right, and so since we have a combination of 3 and 2, so of the 5, we have 3 bonds and 2 lone pairs, and so the shape is T. It's a T shape. And so in terms of the bond angle for T shape, notice how this right here looks like it's 90 degrees. And so the bond angle is just less than 90 degrees. It's less than this value. All right, and so let's go ahead and put that in. So it's going to be T shape. $90. All right, how many more of these things? I think just, is there 12? Are we halfway done? No, there's 10. Oh, okay, good.
Is this essentially what we are doing here? If you look at my camera.
Yes, exactly.
Okay.
Yep, perfect. All right, so only 5 more, guys. We're halfway done. And then we have to go back and do the 3D sketch and the pictures or the models. Anyways, XCF4, so we have xenon and then fluorine. There's 1 xenon, there's 4 fluorines. Xenon is group 8 and fluorine is group 7. And so here, what we have in total is, what is this, 36? All right, so we have 36 valence electrons to place. And so between xenon and fluorine, which is the central atom?
Xenon,
Good. For what reason?
least electronegative.
Good, so it's least electronegative. All right, and so we have xenon right in the middle, and then we're gonna go ahead and surround it with 4 fluorines. Doesn't really matter how you guys distribute the fluorines, it just needs to go around xenon. And so the first step is to make sure that all surrounding atoms, regardless of the identity, except if it's hydrogen, because hydrogen is a duet, it contains 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. And so how many electrons did I just use?
$32.
Okay, 32. So here we have 4 electrons. 36 minus 32 is 4. So 4 electrons remaining. And so how does this translate to lone pairs?
2 lone pairs.
So I'm going to put 1, 2, 3, 4. Okay, so I have 1, 2 lone pairs. Excuse me. All right. And so if we look at our central atom is xenon. It is not part of func. And so that means that to check our draft, we need to determine whether or not we need double bonds or triple bonds, we need to calculate formal charge for xenon. And so I'm just going to go ahead and copy and paste the formula here. So calculate formal charge for xenon. And so how many valence electrons does xenon originally have?
8.
8, good. And so how many bonds do we see in this Lewis-Dot structure?
4.
Okay, 4. So 1, 2, 3, 4. Okay. And then how many are non-bonding electrons?
4.
4. So 1, 2, 3, 4 are non-bonding. And so 8 minus 4 minus 4 is 0. So this calculation tells us that there's no double bonds. I'm just going to put no double / triple bonds. Okay. So in other words, this structure is correct as it is. So here I have Xe, 2 lone pairs, and then fluorine, 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 fluorine. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so this is what our Lewis structure would look like. Excuse me. If we were to translate the bonding electrons, the dots, into lines. Okay. And so let's go ahead and talk about electron geometry. Focusing on xenon, how many groups of electrons do we have?
6.
Right, 1, 2, 3, 4, 5, 6. So there's 6 groups of electrons. So what is the electron geometry?
So octahedral.
So 6 groups. So it's octahedral. And then the bond angle is going to be 90 degrees all the way around. Okay. I want to explore octahedral in a 3-dimensional simulation. It's hard to do it in 2D. So we'll explore that shape later. So for molecular geometry, how of these 6 groups, how many of them are bonds and how many of them are lone pairs?
4 bonds and 2 lone pairs.
Okay, very good. So just to show this for the camera, or not the camera, the recording, there's 2 lone pairs here, and then 4 bonds. Okay. So, sorry, 4 bonds, 2 lone pairs, and according to your chart, what's that combination?
A square planar.
Exactly. All right, so here's 6. And then of the 6, we have 4 bonds and 2 lone pairs. All right, square planar, bond angle is 90. All right, cool. So that's done. Any questions on this, guys? Okay. So as I'm going through more of these examples, are we feeling confident? Or maybe you guys probably felt confident before this. Feeling okay?
Yeah, more and more.
Okay. All right, so let's go ahead and take a look at the next example, SO2, sulfur dioxide. So same situation here, same process, listed out, sulfur, oxygen. We have 1 sulfur, 2 oxygens. What's the group number of both sulfur and oxygen?
6.
All right, and so here we have 6, and then 6 times 2 is 12. Total would be 18. So you have 18 valence electrons to place. Between sulfur and oxygen, what's central?
Sulfur.
For what reason?
It's the least electronegative.
Least electronegative. So you guys can look at your electronegativity chart to determine that.
I just got a quick question.
Yeah, go for it.
Okay, so like H2O, SO2, CO2, are you ever going to have a situation where there's like 2 on one side, or is it always going to be like the single in the middle and then the 2 on the outside, or do you have to go off that electronegativity chart?
Oh, like when I'm placing the oxygen?
Yeah, like obviously not for this one, but let's just use this one for an example. Would it ever be like S and then the 2 O's on the right side or something?
Oh,
Or
no, never.
Can you just look at the formula and just know that S is going to be in the middle?
Yeah, so typically the way that your chemical formula is actually written down, typically, except there are exceptions, and H2O is an exception. The first element, basically your cation, or so typically the first element, if it has less than, if it's the least in quantity, that's going to be your central atom.
Okay, yeah, I think that's what I was getting at. So like take SF6, I can just assume that S is going to be the central atom.
Yes, correct.
Okay.
Yep. But the exception to that is H2O, right? And so the first element is hydrogen, but hydrogen can never be a central atom.
Right, okay.
Yeah, so good. And so, oh, looks like you're ahead. That's awesome. Yeah, so if you guys are if you guys want to try this out on your own, just work ahead, feel free to do so. And so let's go ahead and do the octet stuff. So here I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. And so this is my Lewis dot structure for SO2. Now I'm going to go ahead and check how many valence electrons I have remaining. So I have a total of 18 valence electrons, and I've placed 8 times 2, that's 16 valence electrons used. Then I have 2 remaining. And so how many lone pairs do I have, and where does it go?
One lone pair, but does it matter if it goes like on the top or the bottom?
No, it doesn't matter as long as it's on the central atom itself.
Okay.
So one lone pair on the central. So good question. Let's see here. So I'm just gonna put one lone pair at the very top. If you guys want to put that lone pair at the bottom, it doesn't matter. These molecules are in 3 dimension, and so I can rotate it, flip it, whatever, and it'll be the same rendition as if I were to reflip it or going back to its like original structure. Anyways, so if you guys are looking at the central atom, it's sulfur. Sulfur is not part of func, and so what do I need to do?
Calculate the formal charge.
Mm-hmm. And so I'm going to go ahead and paste the formula for formal charges. And this time I'm solving it specifically for sulfur. It's always a central atom that you're checking the formal charges for. In Chem100, you guys will be using formal charges to determine the overall charge of the peripheral atoms. So that way you understand why phosphate is -3, but I don't need that. I don't need you guys to know that for Chem100 right now. So we're just using the formal charges to determine whether or not we need double bonds, triple bonds. So original number for sulfur is 6, number of bonds.
It's 2 bonds, but 4 electrons, right?
So here, number of bonds is 2. You're absolutely right. So 1 bond, 2 bonds. And then number of non-bonding electrons.
2.
Mm-hmm. And so the non-bonding electrons is like the pink dots. So we have 2. And so 6 minus 2 minus 2, that's going to equal to what value?
2.
Positive 2. Okay. So this is the first instance that when we're calculating the formal charge, that the value is not 0. So what this means is that we need 2 double bonds. And the reason why, so actually the other option is to have 1 triple bond. Now, because there are many sources of lone pairs surrounding the central atom, this is highly unlikely to form. Okay. So the more sources of lone pairs you have in the surrounding atoms, the more likely you're going to form double bonds versus triple bonds. Does that make sense? Okay. And so I'm going to go ahead and erase this triple bond. And so I'm going to go ahead and just move the structure up, because there's going to be several iterations that we're going to do. And so what our goal is, so if you have a formal charge of +2, your goal is to bring this down to 0. When you guys bring the formal charge to 0, then that means that you have the correct structure for your Lewis structure. And so right now we have a +2. And so I'm going to go ahead and do this because it sounds like there's a few students here who's not in my class, in my lecture. And it's good to review anyways, because we did Lewis structures in lecture a couple weeks ago. So I'm going to take this lone pair. You can actually choose any lone pair that you want. You can choose this lone pair. You can choose this lone pair. It doesn't really matter. I'm just choosing this lone pair because it looks like a colon and it fits right in, okay? And so I'm going to take this lone pair and then place it right in between sulfur and oxygen. And so what I want to do is I want to recalculate my formal charge based on the current Lewis dot structure that I have. And so original number of valence electrons is still 6. Number of bonds is still 2. So I have a single bond and I have a double bond. A double bond, much like your electron geometry and molecular geometry, only counts as 1. So I have 2. Now the number of non-bonding electrons is going to be, oh, actually, no, I take that back. Sorry, apologize. Number of bonds would be 3. Okay, so here I have 1, 2, oh, sorry, 1, 2, 3. Okay. So I have a total of 3 bonds. And then number of non-bonding electrons, that still doesn't change. It's 2. So if you guys look at the calculation, I have 6 minus 3 minus 2, that's +1. So notice how by creating a double bond, I reduce this value from +2 to +1. Okay. And so if we have a value of +1, that means we still need 1 more double bond. Okay. And so we're going to go ahead and repeat the same thing. I'm going to take this and place it in between sulfur and oxygen. And then since I've changed some numbers here, or since I've moved that electron, that lone pair, since I moved this lone pair in between sulfur and oxygen, we need to recalculate the formal charge for sulfur. So let's see here, original number of valence electrons is still 6 for sulfur. That will never change. The number of bonds will change. So we have 1, 2, 3, 4. So we have 4 bonds. And the number of non-bonding electrons still the same. We didn't touch it. It's 2. Okay. So 6 minus 4 minus 2 is 0. Okay. So now notice how by creating 2 double bonds, our overall formal charge is 0. Okay. And so this tells you that this is the correct Lewis dot structure for this molecule. And you guys will not know that you have 2 double bonds without calculating formal charges. Okay, and so if you guys are looking at the number of electrons surrounding sulfur, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice that sulfur breaks the octet rule, right? And it can break the octet rule because it's not part of FUNC, F-O-N-C. Now, if you guys are looking at oxygen, I didn't break the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. If you look at the other oxygen, I didn't break oxygen's octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So any electrons between 2 elements or 2 atoms are being shared. So I can double count these electrons for both sulfur and oxygen. Okay. And so any questions on this? All right, and so if your formal charge if your formal charge is +1, then that means that you need 1 double bond. If your formal charge is +2, you have 2 options. You need 2 double bonds, or you have 1 triple bond. If your formal charge is +3, you can have 3 double bonds, or 1 triple bond and 1 double bond. And so it's very rare that I see formal charges above 3. It can happen. But your triple bond option is very, very rare. For you to create triple bonds, there literally is no other lone pair from a surrounding atom that you can pull from. So you always prioritize creating your double bonds. I'm sorry. You always prioritize creating double bonds. And if you can't get the formal charge to 0, then explore triple bonds. Does that make sense? All right, so let's go ahead and talk about electron geometry. How many things surrounds the central?
5.
How many groups of electrons surrounds the central?
Five.
So in this case, a double bond counts as 1 group. So a double bond counts as 1 group, a triple bond counts as 1 group, a lone pair counts as 1 group, a single bond counts as 1 group. And so here I have 1, 2, 3 groups. So 3 groups is trigonal planar. And bond angle is 120. And then of these 3 groups, how many are bonding? How many are lone pairs?
2 bonding and 1 lone pair?
Yep.
So bent?
Yep. Oops. And so for bent, that would be just less than 120. All right, so this one kind of took a while because it's our first time dealing with creating double bonds, triple bonds, but hopefully you guys can understand the process. Hopefully you guys understand the process. Okay. All right, so next one is hydronium. And so looks like this is another first for us. We have a positive charge, so let's go ahead and explore how this is going to work. So total number of electrons, hydrogen, oxygen. We have 3 hydrogens, group 1, oxygen. We have 1 oxygen, group 6. And so here we have 3 plus 6, so that's 9. Okay. So according to our calculations, we have 9 valence electrons. Whenever you guys are working with polyatomic ions and there is a charge, you need to incorporate the meaning of the charge in your total valence count. And so since H3O is positive in charge, what does a cation mean?
It means it loses 1.
Exactly. So cation
Sorry.
lose electrons. No, very good. So cations lose electrons. Anions gain electrons. So therefore, you're going to lose the value that is presented here. So since it's +1, then that means you're going to lose 1. And so your total valence count is not 9, it is actually 8. Okay. Does that make sense? Okay. So central atom, only one option, that's oxygen. Hydrogen can never be central. So let's go ahead and explore what this looks like. So here I have OH3 or H3O. And so since we're dealing with hydrogens again, it can only have a duet. So I have 8 total. Minus 6 used. So I have 2 remaining. So therefore, this is going to be translated as 1 lone pair. Okay. Let's see here. And so let's go ahead and calculate, what else am I missing here? I'm not missing anything. So let's go ahead and just check our work. So here we have the duet, duet, duet. We're looking good. For oxygen, here, since our central atom is oxygen, oxygen is part of FUNC, FONC. And so that means that we want to have the octet. We don't need to calculate the formal charge per se. So if we circle around oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8. So octet. So oxygen already has its octet. So this is its final structure. Okay. Now, you guys are probably gonna be like, why are you doing formal charges? So just very quickly, this is for Chem100. I don't know if you guys have ever asked yourself, but why do polyatomic ions have the charge that it has? It doesn't really follow any rules from the periodic. And so the charge for the polyatomic ions actually is derived from the formal charge of the Lewis structure. And so I'm just going to go ahead and show you guys just one time here. And so if you guys calculate the formal charge for oxygen, we have 6 original, I have 4 bonds and 2 lone pairs. I'm sorry, oops, not 2, 3. Okay. So I have 6 original valence electrons for oxygen, 1, 2, 3 bonds for oxygen, and 2 non-bonding electrons. And so if you guys calculate the formal charge, this is +1. This is the reason why the overall charge for hydronium is +1. It's from the formal charge. Okay. So there's really no way to memorize charges other than just drawing Lewis structures and calculating formal charges. But at that point, you might as well just memorize the charge of those polyatomic ions. Okay.
So you can't get it down to 0 because there's no other groups to pull from.
Exactly. So here, there's no lone pairs on hydrogen. So we cannot get this down to 0. All right. So basically, this is the reason why hydronium is +1. And so since we're dealing with a polyatomic ion, when you guys are drawing the final Lewis structure, you guys need to put a bracket to communicate to the reader that hydronium has an overall charge of +1. So if for those who have me for lecture, I actually really don't care about the brackets. I just want you guys to draw Lewis structures. But for those who are moving on to Chem100, this is technically your final answer. And it might have it in Alta too. Okay. All right, so let's talk about electron and molecular geometry, the easy stuff. How many groups am I working with for hydronium?
4.
1, 2, 3, 4. So that's tetrahedral. Bond angle is 109.5. Molecular geometry.
It's trigonal pyramidal.
Correct. So the combination is 3 bonds, 1 lone pair. So this is trigonal, pyramidal. And this is less than 109.5, the bond angle. So once again, I got all of this from the reference that's provided in the lab Canvas shell. All right, moving on, guys. So it looks like we have another polyatomic ion. Here we have carbonate. So let's go ahead and quickly go through this. So here I have carbon, oxygen. We have 1 carbon, 3 oxygens. And then carbon group 4, oxygen is group 6. So 3 times 6 is at 18. So here I have a total of 22. Okay. But since carbonate has a 2 negative charge, what does this mean in terms of the total count?
We add 2.
Correct. And so anions gain electrons. And so we are adding 2 electrons. So our total count is 24. Okay. So between carbon and oxygen, central.
Carbon.
Good. So here we're just going to go ahead. Oops. You know what? Let me draw this a little smaller here. We'll put it off to the side. So carbon, and then oxygen, oxygen, oxygen. So same deal. We have to place. We have to make our surrounding atoms octet. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have 24 valence electrons, and we used 24. Okay. So 24 was our total, and we used 24. 8 times 3 is 24. So this tells us that we have 0 lone pairs on central atom. And so looking at the structure, we do have octets on the surrounding. The surrounding is happy. If you look at the central, we don't have an octet. And since the central atom is carbon, carbon is part of func, we need an octet. And so what do?
We have to make a double bond.
Mm-hmm. And so there's so many sources of lone pairs from oxygen that you guys can choose from. It doesn't matter which oxygen because they're all the same. So just choose one and then just move it between carbon and oxygen. So I'm going to choose the oxygen at the top. And then I'm just going to go ahead and move it between the oxygen at the top and the carbon. And so if I draw a circle around carbon, I have 1, 2, 3, 4, 5, 6, 7, 8. So carbon has the octet rule. This oxygen also has the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Remember, these electrons are being shared, so you can double count them depending on the perspective. All right. And so let's see here. We're going to go ahead and translate this. Sorry, guys, I'm slowing down. I'm going to translate this like this. All right. And so I can just go ahead and put a bracket and put in 2 negative. Okay. Now, for this example, if you were to calculate the formal charge for oxygen, the formal charge of, I'm sorry, if you guys were to calculate the formal charge of carbon, the formal charge of carbon is 0 in this specific state. And so where is the negative coming from? The negative is actually coming from the formal charges of these two oxygens. And so I can go ahead and quickly prove that to you, just very quickly here. If we're trying to calculate the formal charge for these two oxygens, I just need to calculate it one time because the bonding pattern is the same. So the original number of valence electrons is 6. Number of bonds is 1, right? So I have 1 bond between carbon and oxygen. And then number of non-bonding electrons, that's 1, 2, 3, 4, 5, 6. Okay. And so overall, 6 minus 1 minus 6, that's -1. And so the formal charge for this oxygen is -1. And since the bonding pattern is the same, the formal charge is the same for both of these oxygens. So -1 plus -1 is -2. This is the reason why carbonate has an overall charge of -2. It's from the formal charges of the surrounding atom. All right, so that was just another application since we're dealing with polyatomic ions, but you guys don't need to really, what's happening here? So you guys don't really need to showcase that in your Lewis dots, in your, what is this, worksheet? If you guys wrote it down, that's fine. I mean, I'm the one who's grading it anyways. So electron geometry, what would this be?
Trigonal planar.
Very good, trigonal planar. Remember the double bond counts as 1 group. So you have 3 groups in total. What's my molecular geometry?
Also trigonal planar.
Also trigonal planar. What's the bond angle in trigonal planar?
120.
Very good. All right, almost done, guys. All right, so this is our last molecule. So CH3OH. Let's go ahead and just kind of work through this. Here we have 3 elements this time instead of 2. So I have carbon, hydrogen, and oxygen. You have CHO. So I have 1 carbon. How many hydrogens do I have?
4.
4. Oxygen.
1.
And so carbon is group 4, hydrogen is group 1, oxygen is group 6. So 4, 4, 6. So here we have 14 in total. Now between hydrogen, carbon, and oxygen, of these 3 elements, what's central?
Both C and O.
Okay, correct. Here in this case, it did tell us that we have 2 central atoms. And the way that you guys are going to draw this Lewis structure is kind of basically it's going to be very similar to how it's written out from left to right. And so if you guys are going to organic chemistry, this will be a little bit more clear, but OH is a hydroxyl group. And so this hydrogen is going to surround this carbon, and then this carbon is going to be connected to this oxygen. And then this hydrogen is going to be connected to this oxygen. And so if you can, if you make a squiggly line, it kind of shows how things are going to be grouped. And so here you have carbon, and then you have oxygen. Both of these are our central atoms. And then what surrounds our central atoms is going to be hydrogen. So we're going to have 3 hydrogens surrounding carbon, as indicated in the organic formula, so CH3. And then you're going to have 1 oxygen, I'm sorry, 1 hydrogen attached to the oxygen. So this is our Lewis dot structure. Any questions on this one? So for those who have me for lecture, I will not give you one with two central atoms. We're working just very simply. So this is just an exercise for lab. For those who don't have me for lecture, ask your lecture instructor. All right, so let's see here. I have 1, 2, 3, 4, 5. So 5 times 2 is 10. So of the 14 valence electrons total, I use 10. I have 4 electrons remaining. And so how many lone pairs can I create out of this?
2
And where do these lone pairs go?
on oxygen.
On oxygen. And so the reason why it's going to be on oxygen is because if you guys look at carbon, carbon already fulfilled its octet, right? And if you look at oxygen, oxygen only has 2 bonds. So that's 1, 2, 3, 4. And so by having 4 more attached to oxygen, it also fulfills its octet. Okay. And so this is our Lewis dot structure. Now, whenever you guys have multiple central atoms, that means that the electron geometry and the molecular geometry is going to have to be defined for both. So I know that it says electron around C, but we're actually going to do both. And so when we're looking at carbon, we have 1, 2, 3, 4 groups of electrons surrounding it directly. And so the electron geometry for carbon is what?
Tetrahedral.
And we know the bond angle is 109.5. What about the molecular geometry for carbon?
Also tetrahedral.
Same thing. So of those groups, of those four groups, 4 of them are bonding, 0 lone pair. Okay, so that's the definition for, that's how we got tetrahedral for molecular geometry. Now for oxygen, since oxygen is a central atom, we can also define its molecular or its electron geometry and molecular geometry. And so what is the electron geometry for oxygen?
Tetrahedral.
So same idea, we have 4 groups, 1, 2, 3, 4. So I'm just going to go ahead and copy this. Okay. And then for molecular geometry, what would it be? So of the,
Sorry.
No, you're good, you're good. So of the 4 groups, we have 2 bonds or 2 bonding and 2 lone pairs. And so that would be bent for molecular geometry. That's less than 109.5. Okay. Oh, whoops, I didn't zoom out. I kind of already answered both. Okay. All right, and so any questions in regards to that? Okay, awesome. So we're gonna go ahead and take out our, what is it called? Molecular models, and we're gonna go back to number 1 here. And we're gonna go ahead and start drawing the 3-dimensional sketch. So just give me a second, I have to find my molecular model. I don't know where I threw it. How are you guys holding up?
Good so far.
a long one. It's always a long one. All right, so hopefully you guys are excited for those who are moving on to Chem100. You guys are actually going to go back into lab next semester, so you don't have to hear your instructor talk for 3 hours. All right, so I'm going to go ahead and take out my model. So I believe the very back of your piece of paper, it has a key. So it describes, what color is a specific element. So hydrogen is white, carbon is black, oxygen is red, nitrogen is blue, sulfur is yellow, phosphorus is purple, fluorine is orange, chlorine is green, bromine is dark blue.
Ours doesn't have that, or at least mine doesn't.
Oh, okay.
Barry, did yours come with a little like pamphlet?
Yeah.
I think it's on the inside of the first page.
Oh, okay. I was looking at the one on the screen. Okay, gotcha.
Yeah, I was looking for that one too.
Oh, sorry. Yeah. This molecular model was given to me like when we first did online labs. And so I think there's many suppliers that we're pulling from. So I don't know what you guys have. All right. So the only thing I disagree about this current key is the use of bonds. Your longest bond, oops. So your longest bond is going to be your single bond, always and always. And so let me show you the bonds that I have. I don't know if you guys can see it on the screen here. Oh, oh. Here. All right. So these are the 3 bonds that I have for my molecular model, my 3 connectors. Your single bond will always be the longest. Your double bond is second longest, and then your triple bond is the shortest. And so I'm not too sure what type of molecular model was given to you and what your key says, but whatever your key says, if it is not in line with what I had just said, then it's wrong. So the longest bond is a single bond, middle bond is your double bond, and your triple bond is your shortest bond. Okay, and so just go ahead and keep that in the back of your mind. For those who are moving on to Chem100, you guys will know more about why single bonds are the longest bond compared to the rest. So anyways, the first item that we're going to do is water. With water, it's just H2O. You're going to go ahead and connect 2 white spheres to H2O. So just take a red sphere, attach it to 2 of your longest, use 2 of your longest bonds, and then attach 2 white spheres at the end of it. So this is your molecular model of what water looks like. Now, it's not anything to look at, but if you guys recall, the molecular geometry for water is bent. This is the bent feature. So notice how the shape of the molecular geometry only takes in consideration the bonding groups, not the lone pairs. So you guys can imagine that there's 2 lone pairs up here, but it's not shown. Okay. And so when you're talking about the bond angle here, this is going to be less than 109.5. In terms of the perspective drawing, if you guys are viewing it in this perspective, notice how the white sphere is in line with the red sphere. The white sphere is in line with the red sphere. And so you guys would use normal lines for your 3-dimensional depiction. Now, if I were to rotate it in this perspective, if you guys are looking at my camera, notice how this bond or this white sphere under this rotation is above, or it's in front of the red sphere. And so this white sphere is behind the red sphere. And so if you guys are drawing it under this perspective, then this bond is going to be a wedged line, and then this bond is going to be a dashed line. Okay, so there are two perspectives that you guys can use. Actually, there's more than two perspectives. And so what if my perspective is like this? Okay, so remember, everything is in respect to the central atom. So with respect to the central atom, how would you depict the bonds in a three-dimensional perspective using this?
Two wedges.
Two wedges, exactly. And then if you are, if this is your perspective, where this central atom is right here, and then these are your surrounding atoms, what would the bonds be? How would you represent the bonds? The bonds would be two dashed. So all you guys are going to do for your three-dimensional structure is choose one perspective and then just represent that. So your 3D sketch should match your molecular model picture. And so I am actually just going to do, so this is going to be my molecular model picture. This is my perspective. I'm going to go ahead and choose red. Okay, so this is my oxygen. And so I'd love to choose white. But anyways, the perspective that I'm going to choose is this. Oops. Let me see if I can do it much better. Okay. I know that the perspective, so you guys don't need to draw, you guys just need to take a picture of this. But basically, this hydrogen is in front of the central carbon, and then this other hydrogen is behind. And so the perspective that I'm going to take a picture of, if you will, is going to be this. Okay, so this is what I'm basically trying to depict. Okay. And so if this is the picture that I'm going to take for water, then my three-dimensional perspective, or my 3D sketch, would be hydrogen is going to have a wedged covalent bond, and then the other hydrogen is going to have a dashed bond, and then that's all I need to depict. And so your lone pairs, you guys can just go ahead and draw it, and that'll be that. Okay. And so your 3D sketch should match your molecular model picture, the picture of it that you're going to take. Any questions?
Why did you do the lines instead of, like, why did you do a shadow looking thing in the lines?
Oh, so this is known as a wedged bond. So wedged bond means that the atom that connects it to, that it's connected to, is going to be above the central atom. So it's in front of the central atom. And then this line, so it's a dash line, basically means that this hydrogen is behind oxygen. It's furthest, this hydrogen is furthest back.
So what if we did it with the regular bent with the oxygen on top? What lines would we use then?
Okay, so the oxygen like this. Hold on real quick. Like this. Is this your perspective?
Mine is the oxygen on top and then two H's on the
this?
bottom. Yes.
Like this? Okay. So that means that give me a second. Need my stand. And so if this is your perspective, this hydrogen, and so these two hydrogens are in plane with oxygen. So if they're in plane, then that means that this is a normal line and this is a normal line. And so how you're going to translate that, if that is your perspective, is just oxygen with your two lone pairs and then just two normal lines. And that's also acceptable. Right? So when you're using a normal line, then that means that this atom is in the same plane as the central atom. Everything is in respect to the central atom.
Now, does it matter if the lone pairs are sitting where they are? Or could they be down below?
Oh, yeah, yeah, they can be down below.
Okay.
Yep. All right, so let's go ahead and move on to the next one. This is CH4. So this is tetrahedral. So we have carbon and hydrogens. So we're going to go ahead and take a black sphere. Then notice that there's 4 holes. So 1, 2, and then 3, 4, where you guys see the bonds are sticking out. So we're going to go ahead and use one. That must. So here, so here I have 4 bonds, and then I have my hydrogens. So hydrogens are white. Okay. So this is going to be my back. So this is my my methane CH4. This is a tetrahedral conformation. So when we're talking about bond angle, we're talking about the bond angle here. So from here, it's 109.5. And then if we were to rotate it, this bond angle is theoretically 109.5. This bond angle is 109.5. This bond angle right here is 109. This bond angle here is this bond angle is 109.5, and then this bond angle is also 109.5. And so if we're trying to represent this as a 3D structure, so let's go ahead and do this perspective. Okay. So this is the central. How would I represent this bond?
With a wedge.
Okay, so this is a wedge because this hydrogen is in front of this carbon. Then how would I represent this bond back here?
Dash line.
Dash line. And so let me see if I can. So for this hydrogen, is it in the same plane as this carbon?
No.
Oh
wait, the top one or the right one?
The one at the top.
Oh, yes, it is.
Yeah. And then the one on the right, is it in the same plane as this carbon? And so to see if it is, we're just going to rotate the camera. So notice how these two hydrogens is in the same plane as this carbon. So that means that the line we're going to be using for these two hydrogens are normal lines. So this is normal, then this is a normal line. Because the original perspective is this. This is the original perspective. I just moved the camera around so that way we can see that these two hydrogens are in the same plane as this carbon. And so under this perspective, I have two normal lines, one dashed, and then one wedged. Now, if I were to change my perspective so that it looks like this, okay. So what would, oh man, I can't. Sorry guys, I wish I had like 3 arms. How many normal lines will we have under this perspective?
1?
There's actually none.
Oh, none.
Yeah. And then how many wedged lines do we have under this perspective?
1 wedge.
Yes. And so, sorry, I forgot I can actually just zoom in closer. So this right here would be wedged because this sphere is in front of the black. If I were to rotate, I'm going to keep my conformation and I'm going to rotate, right? So notice how, excuse me, under this perspective, right, all 3 of these hydrogens are sorry, I don't know if you, all 3 of these hydrogens are slightly behind the plane of this carbon. So if you're looking at it from the top down, then all 3 of these would be dashed. Okay, and so we're only focused on drawing one depiction of tetrahedral, but I just kind of wanted to bring that into light. So basically, if you guys are taking this perspective and looking at it from the top down, notice how this black sphere is above these 3 white spheres. And so if your perspective is looking at it from the top down like this, then these 3 bonds would be dashed, and then this is a bold, or I'm sorry, a wedged. But if the perspective of your 3-dimensional drawing is how you guys see it right now, then these 2 would be normal, and then this is bold or wedged, and then this right here is dashed. Does that make sense? Hopefully I didn't confuse anyone. Okay. And so this is the depiction that I'm going to use, where these 2 hydrogens are normal because they're in the same plane as this carbon. And then this is dashed, and then this is wedged. Okay. So for my 3D sketch, here's my carbon. I have 2 hydrogens that are in the same plane as the carbon, so normal lines. 1 hydrogen is in front of the carbon, so that's wedged. And then 1 hydrogen is behind the carbon, so that's dashed. Okay. Does that make sense? Okay. So just make sure that you guys are taking a picture that represents the 3-dimensional sketch. All right, so next we have CO2. So we have carbon and 2 oxygens. All right, so actually, you know what, for this one, I'm going to be using, yeah, why not? I'll go ahead and use, I already like pre-made some of these. So instead of, so I'm going to go ahead and use this for CO2. So instead of using these shorter bonds, I'm actually going to go ahead and use 2 single bonds. And then I am going to connect it to oxygen. And so that way you guys can kind of see how the double bonds kind of interplay. So here I have black that represents carbon. Here I have oxygen. It's represented by the red. And so to create a double bond using 2 long bonds, I'm just going to go ahead and bend them. So you guys, when you guys are bending them, you can kind of feel the strain. So this strain that you guys feel is represented in, shoot, there it is. Okay. And so when you guys are forming double bonds, you kind of already feel a strain forming them, right? It's not very easy. And so this is, if you guys can imagine triple bonds, that's even more strain than a double bond. So this is the reason why double bonds are preferred to be drawn first versus triple bond. You should only form a triple bond if you can't pull lone pairs out of any other surrounding atom besides the one that it's currently bonded to. And so we're going to go ahead and I'm going to go ahead and do this again. Let's see, just give me a second. So instead of using the shorter bonds, I'm just going to go ahead and use 2 long bonds to create this 3-dimensional structure. So this is carbon dioxide. Okay. So it's a cool looking structure, right, compared to the rest. And so everything is in respect to the central atom. So if I were to lay my model in this fashion, how would I represent these bonds?
Just be two lines in one direction, 2 in the other.
Mm-hmm. So these would be normal lines, right? Because the red sphere is in the same plane as the black sphere. Now, if I were to change my perspective, right? If this is my perspective that I'm working with, how would you guys represent this bond that I'm pointing at right now?
Would it still be one wedge?
Yes, it would be wedged. And then these bonds I would be representing as
Dash lines?
dash lines.
So do you only have, for each bonding group, you only show one wedge or one dash line?
Yeah.
Okay, so just because there's it's a double bond, we don't add more?
No. When you're representing in 3 dimensions, no. If you guys want to, you guys can. I'll show you both.
Okay.
And so just choose one depiction. And so if you guys wanted to just represent it in such a way that the oxygens are above the plane of carbon, you guys can go ahead and do this. Okay. Now, if you do want to represent a double bond, you guys can put 2 bold like this, and then 2 dashed like this. Okay. And so this is just a 3-dimensional depiction, right? It's not really, if you guys are doing this, it's not really describing the total number of bonds. They're just saying that whatever this bond is, whether it's a double, single, or triple, it's in front of, this oxygen is in front of carbon. Same idea applies to the oxygen that's going behind carbon. But if you do want to be a little specific, there's nothing stopping you from doing 2 bolds and 2 dash. Same thing with triple bonds. Now, if your perspective is just the flat version of CO2, then it's just 2 normal lines. Okay. All right, any questions on CO2? Oh, don't forget to put in lone pairs. Oh, whoops. Okay. So once again, you guys are going to take a picture of your CO2 and either somehow paste it on this in this space without changing the format, or just putting it in a different Word document and then uploading two documents. All right, so BF3, boron. Do I have a gray? I think I have a gray. So for boron, trying to find, okay. So boron on my end is a gray sphere. I think you guys might only have one, or two. I'm not too sure. Oh, sorry. So just look around, dig around your molecular model. We're looking for a gray sphere that has 3 holes. So here I have 1, 2, and 3. Okay. 3.
Professor?
Yeah.
So we do have the boron, we have 2 of them, but we do only have 2 of the fluorine. Should we just use another color that has the same amount of holes?
You're right. Yep.
Okay,
So yeah, no problem. So your fluorine is orange. So here I have 1, and then we do another single bond here. Yeah, so thanks for bringing that up. Since you only have 2 oranges, you can just go ahead and use any other color really to represent that last one. Unfortunately, actually, you know what? Let me do red. Or same number of holes. I kind of want to just do it with the same hue or same coloring. So let's just do red. Even though there's a whole bunch of there's another hole for red, but it's not too bad. Not a bad substitute.
So I don't have any orange. Would it be okay if I used, I don't know.
Just pick a color.
Okay.
And so do you have greens? Because greens also has 1 hole.
Yeah, I've
that's
got
what I'm
green.
using.
Right. And so I'm just going to go ahead and choose red just because they're kind of the same color as, same hue as orange, right? So maybe I can kind of get away with it if I were to push it back. So this is your BF3. Let's go ahead and look at it in this perspective. And so what would my bond be here? How would I depict this?
Wedge,
Okay. Wedged. What about this one?
dashed.
And then this one?
If you're trying to go with a regular line, I guess.
Yeah. So it's better if you look at it from the top down. Notice how the gray and the orange on the right is like in the same plane. Where's my Apple Pencil? Right. So they're kind of in the same plane. They match up. So BF3 is supposed to be trigonal planar. Right now, it doesn't look trigonal planar, but if you push this down, notice how it's basically flat. Okay. I know that I'm kind of fudging the normal shape of this, but trigonal planar is supposed to be flat. So there's 3 sides and then it's 120. So if I look from the top down, this bond angle is 120, this bond angle is 120, this bond angle here is also 120. Okay. So let's go ahead and quickly do this. So 3D sketch. So you have boron with one normal line, 3 lone pairs. You have fluorine, dashed line, 3 lone pairs, 1 bold or 1 wedge, 3 normal, 3 lone pairs, sorry. Okay, that's pretty much it for BF3. Any questions?
That's the front view of the
Correct.
model, correct?
Yep.
Sorry,
this
I
is the-
can't think of words.
No, you're good. Actually, that's the proper word for it. It is the front view. I just can't think of words, so you described it perfectly. All right, so CLF3, I'm going to be honest with you. For the 3-dimensional sketch, it's going to be the same as BF3. And so we're just going to pretend that for CLF3, this is CL, and then this is the fluorine. Okay. Oh, wait, hold on real quick. No, because we're talking about trigonal bipyramidal. Darn. Right, so trigonal bipyramidal, look for dark blue sphere. Sorry, I kind of jumped the gun on that one. So CLF3, look for your dark blue sphere. And then I want you guys to connect. So break down your oranges and red or whatever color you guys use for BF3. And so for CLF3, the molecular geometry is T-shaped. Okay. And so notice that here you have a shape of a T. And then remember that CLF3 has 2 lone pairs. Well, the lone pair is represented by that empty slot, if you will. So this is 1 lone pair, and then this is another lone pair. So you have 2 lone pairs here, and you have 3 bonds. And so this is a T-shaped molecular geometry, but the electron geometry is trigonal bipyramidal. And so for you guys to see the bipyramidal, feel free to just add, you know, I'm just grabbing some random stuff now. So this is going to be trigonal bipyramidal. Sorry, just give me a second. Okay. Let me see if I can prop my iPad, or yeah, my iPad up just a little bit here. So this right here is trigonal bipyramidal. If you guys are looking at axial to equatorial, this bond angle right here is 90 degrees. If I rotate it this way, this is 90 degrees. If I were to rotate it this way, it's 90 degrees. And so same thing, if I look upside down, this is 90 degrees. If I were to rotate it this way, 90 degrees. All right, so anything axial to equatorial is 90. And so if I look at it in this perspective from the top down, notice that this forms a circle, right? If you were to connect the vertices, the 3 vertices here, so this bond angle is 120. So equatorial to equatorial is 120. This is 120. This is also 120. So this is your trigonal bipyramidal. Also, if you're going from axial to axial, what's the bond angle between the axial and axial?
180.
180, correct. So this is just half a circle. So the bond angle here is 180. So let's get back to the T-shaped. Let me remove the white and the black, so that way we can best represent. So I remove the white and the black, and what I have is the molecular geometry T-shape. If you guys are doing it in this perspective, the front view, any wedged or dashed lines?
No.
No. So they're all normal lines. And so if I were to change a perspective like this, what would this bond be?
Solid wedge.
Wedged. And then this is
Dashed.
dashed. And then this is
Normal.
normal. Exactly. So just pick one perspective. If it's front view, they're all normal lines. If it's in the side view like this, then it's wedged, dashed, and normal. Now, if I do top down, I have 2 normal and then 1 dashed if it's top down. Okay. Now, if it's bottom up, then this is going to be wedged and 2 normal. So just pick one perspective.
You said it's fine if we use different
So-
colors, right?
Oh yeah, absolutely. And so I know that your molecular lab kit is kind of limited on colors and quantity. And so let's just do this very quickly. The perspective that I'm going to choose is the side perspective where there is 1 dashed, I'm sorry, 1 wedged. So this is fluorine, 1 normal, and then 1 dashed. Then I have 2 lone pairs on chlorine. All right. Any questions on CLF3? All right. So here we have XCF4. We're going to go ahead and look at a different central atom. So XE, so that's octahedral. If you look at your key, your octahedral is yellow. So we're going to go ahead and look at, take out our yellow. And at this point, we're just going to surround it with whatever color we can kind of pick up. So let's just be consistent. For this one, I'm just going to choose white. I have more white spheres than any other colors. And so I know that white is supposed to be hydrogen, but you guys do not have 4 hydrogen, or you guys don't have 4 oranges. So I'm going to use hydrogen, use white to represent the 4 fluorines. If you guys don't mind me doing that. So here's another one. Now, the way that you guys are going to develop this molecular structure is going to be a square planar, because that's the molecular geometry that we identified XCF4 to have. And so this is going to be your square planar, where XE, xenon, is going to be the yellow atom, and then the white spheres is going to represent your fluorines. So there's many perspectives that you guys can use. So the holes that is on your yellow sphere is going to represent your lone pairs. So there's 1, 2 lone pairs. Okay. All right. So For this perspective, right, if we're looking at it in this fashion, how many bold, how many normal, how many dashed? Sorry, I keep on saying bold, it's wedged. And so this one would be
Maybe wedged.
wedged. And then this hydrogen
Dashed.
dashed. And then these two
Standard.
normal lines. Now, if I were to rotate it in this fashion, would I have any normal lines?
No.
No. So here I have 2 wedged and 2 dashed. Okay. If I were to look at it from the top down, do I have any wedged or dashed?
No.
No. So all of these would be normal lines. Okay. So once again, just choose one perspective and just take a picture of that and then represent that in your 3D sketch. So for me, I'm actually going to represent it in this fashion where I don't have any normal lines. I have 2 wedged and 2 dashed. Okay. So here's my xenon. This is xenon. And then I have 4 fluorines here. 2 of them are going to be dashed. Another one, I have the other 2 as wedged. And then I'm just going to go ahead and draw in my lone pairs for my surrounding atoms. I'm also going to draw in the 2 lone pairs on xenon. Okay. And I think I did that for chlorine, right? Did I add in lone pairs? Yeah, I did. Let me just fix this. Maybe I'll fix this too. Anyways, cool. So moving on to the next one. So we have SO2. And so let's go ahead and kind of look at that. Actually, real quick, for the octahedral, if you guys were to place, if you guys were to fill in the holes with just any random atoms, kind of looks like this. So this shape is known as an octahedron because overall it has 4 or 8 sides, right? So if you guys can connect the vertices, so this is 1, and then 2, and then 3, and 4. And so since it's symmetrical around the vertical or around the horizontal, we would also have 1, 2, 3, 4. So there's 8 sides in total. So this is an octahedron. So if you guys are looking at the bond angle for octahedron, axial to equatorial is 90. So axial to equatorial is 90. Axial down here to equatorial is 90. Axial to equatorial is 90. If you were to rotate this so that it's top down, equatorial to equatorial is 90. Equatorial to equatorial is 90. Equatorial to equatorial is 90. Okay. And so it doesn't matter how you rotate this octahedron, the bond angle is 90 degrees all the way throughout. All right, so for the next one, it's SO2. SO2 is bent, trigonal planar bent. For the sake of time, because I know I keep on talking, I'm going to go ahead and just use, oops, let me see here. I will go ahead and use the gray sphere. So take out your gray sphere, the one that has 3 holes. And this time I'm actually going to be using a shorter bond to represent a double bond. And so I'm going to go ahead and connect the gray sphere with the slightly shorter bond. And since I have more hydrogens, I'm sorry, since I have more white spheres, I'm just going to represent the white sphere as the, was it oxygen? Oh, SO2. Oh, actually I have enough. I don't have to do white spheres. I can do red spheres. Sorry. So so this is going to be SO2. So the reason why I chose the gray sphere is because we have one lone pair. So here's that lone pair on that sulfur. I'm using a shorter bond just for perspective. We can see that the gray and red bond is shorter than the yellow and white. So this is representing a double bond. This is representing a double bond, a lone pair over here. So this is a bent structure. It's very similar to water. So you guys can have it as a front view. If it's front view, then these are normal lines. If it's side view, you have a wedged and then a dashed. If you have the top down, then this is 2 dashed. And then if you guys have bottom up, if the perspective is bottom up, this is a dash, I'm sorry, this is a wedge, this is a wedge. Okay. So just choose one perspective, front, side, top down, or bottom up. Okay. So I'm actually just going to use, I'll just do something different here. I'll go ahead and choose the bottom up perspective where I have 2 wedged bonds. Okay. So that's the perspective that I'm going to use. All right, so here's oxygen, oh, sorry, sulfur. Sulfur, and so my perspective is from the bottom up. So I'll have 2 wedged, and then I have my oxygens. I'll have 1 lone pair. Sorry, I'm trying to draw this with my stand. That's why it's not as nice as the rest of my handwriting. So something like that. Just make sure that you guys are taking a picture of your perspective so that it matches with your 3D sketch. All right, so that's number 7. Number 8, we have hydronium. So if you guys are looking at the electron geometry, notice that the electron geometry is tetrahedral. And so the molecule, or the color of the sphere that we're going to be using for something that's tetrahedral is going to be the black sphere. And so I know that black sphere is supposed to be carbon, but for this example, what was the molecule again? Oh, hydronium, OH3. We're going to go ahead and use the black sphere because this is our tetrahedral atom. And I'm going to go ahead and connect 3 white spheres to the 3, I'm sorry, to the black sphere. Running out of steam. Can't really think properly. All right. So this is my hydronium. Remember that hydronium has 1 lone pair. So the lone pair is this empty spot that you guys see at the very top. Here I have my hydrogens. And let me see here, the central atom is going to be oxygen instead of the canonical carbon that black is supposed to represent. And so in terms of representation, if we're doing front view like this, notice how this is going to be a wedged. This right here, these two are going to be dashed because they are behind the black sphere. So if it's front view like this, 1 wedged, oops, 1 wedge and then 2 dashed. If it's top down, what would you use?
Regular lines.
Top down. It's
Top down. Okay,
yeah.
so they're all dashed lines.
So top down, they're all dashed. Okay, so you can kind of see that the hydrogens here are kind of pointing down. So they're already below the plane of the black sphere. So if this is your perspective, then all 3 of these lines are dashed. And so if it's bottom up, if you're looking at the bottom up, then all 3 of these are pointing towards you. So all 3 of these are going to be wedged, and there's no normal, no dashed. If you're looking at it in this perspective, where you have this hydrogen in plane with this oxygen, then this is a normal line. This is a wedged line, and this right here is a dashed line. Okay. So just go ahead and choose one perspective. I'll go ahead and just choose the front view perspective, where I have 2 dashes at the very back, and then 1 wedge in the front. So oxygen, trying to do this with my stand.
Now, since this one has a positive charge, would we put it in brackets also like we did for the 2D model?
Yes.
Okay.
And then the lone pair. All right, so only a couple more, guys. Here we have CO2. So notice that the electron geometry is trigonoplanar. So for trigonoplanar, we will use the gray sphere with a 3. So this one right here. So we're doing CO3, right? Or CO2. No, what are we doing? Carbonate. So carbonate has 1 double bond and 2 single bonds. So I'm just going to go ahead and choose the orange because it's already connected to a single bond. Okay. So this is going to be carbonate. it's supposed to be trigonal planar. There is no trigonal planar in your atomic model, unfortunately. And so to mimic trigonal planar, what we're going to do is we are going to push the central atom down so that it's flat. Okay. It will not stay flat if I were to lift my finger, so I'm just going to go ahead and push it down. So once again, you guys can do many different perspectives here. If we're doing, let's just say that this is front view, or actually this technically this is bottom up. So if we're looking at the bottom up, what line would these two represent?
Those would be wedges.
Correct. So these would be wedges, and then what would this bond be at the over here?
Dashed.
Dashed. So you guys can play around with this. If you want to do front view like this, you guys can. If it's front view for trigonal planar, everything is going to be a normal line. And so if you guys are looking at it from the top down, I know it's not flat because we don't have trigonal planar, but if it's top down, this is 1 wedged and 2 dash. So just choose one perspective. I'm just going to go ahead and choose this. 2 wedged and then 1 dashed. So just know that this is a double bond. And so to kind of represent a double bond here, we're just going to go ahead and put in, 2 dashes, right? Just to make sure that you guys link this to this. Any questions?
Doesn't the top O only have 4?
Oh, yes, thank you. Perfect. All right, and so the final one is going to be CH3OH. So you guys are going to be using 1 black sphere, 1 red sphere, and 1 white sphere. Or I'm sorry, not 1 white sphere, 4 white spheres. So here I already have 1 black sphere and 3 white sphere. So I just need, I think I already have it pre-made. Let's switch some stuff out here. Yes, sorry. Trying to figure this out. So I just need a long bond. So here's my carbon with the 3 hydrogens. It's connected to oxygen. Oxygen is going to be red in this scenario. And then I'm going to go ahead and connect this with another white sphere. So this is going to be so this is going to be what is methanol. And so if I move this camera around, you guys can kind of see the different perspectives. You guys can kind of see the 3-dimensional character. So they're both tetrahedral. Both central atoms are tetrahedral in electron geometry, but molecular geometry dictates. So molecular geometry ignores any lone pairs as contributions to the overall shape. And so under molecular geometry, oxygen is bent. So you guys can kind of see the bent structure here, while this carbon is still tetrahedral. So we can kind of see that tetrahedral nature under this perspective here. Okay. And so there's many perspectives that you guys can use to draw. So I'm just going to go ahead and present two. Let's just go ahead and do front view as is. And so if we're doing front view, then we have one wedged. What would these two lines be?
Standard.
Mm-hmm. And then here at the, so where my Apple Pencil is pointing?
Dashed.
Dashed, okay. And then what about this line right here?
Be standard also.
Mm-hmm. Yep, it's a standard or normal line. And so if this is your perspective for methanol, you have one wedged, one dashed, and then 1, 2, 3 standard or normal lines. Okay. Now, if this is my perspective for methanol, these three bonds, they're going to be pointing, they're mostly pointing at you. They're above the plane of the central carbon. So this would be wedged, this would be wedged, this would be wedged. And then this right here is going to be dashed. And then this right here is going to be dashed as well. So the oxygen hydrogen bond is dashed as well. And so if you're looking at it in this perspective, 3 wedged and then 2 dashed. Okay. So just go ahead and choose one. I'm just gonna go ahead and choose the front face, the front view. So overall, I have carbon in line with the oxygen. Oxygen is in line with hydrogen. This carbon is also in line with one of the other hydrogens. And I have one wedged to a hydrogen and one dashed to a hydrogen. Okay. And then I'll just fill in my lone pairs on the oxygen, and that's that. Any questions on the 3D sketch? And so I know that this is a long lab, and I really haven't given anybody breaks, just me talking for 3 hours. Does this, hopefully this exercise kind of helps in terms of drawing Lewis structures and drawing the 3-dimension and identifying electron molecular geometry. So there is one other thing that I do want to show you guys as a tool to help you explore the 3-dimensional character of, let me see here. So if you guys were to just type in PHET, P-H-E-T, let's do Lewis structure. There is a molecular shapes simulation. And so you guys can do model or real molecules. I'm going to go ahead and choose real molecules. So if you look at this website, it kind of shows, you guys can check off molecular and electron geometry. It shows, actually you can also check off bond angles. So remember that the molecular geometry for water was bent, and I said it was less than 109.5. Well, that exact value is 104.5. So you guys don't need to know this piece of information. You just need to know that if there are lone pairs present on your central atom, then the theoretical bond angle is going to be less than what it should be. And so you guys can look at CO2. So notice how CO2 is linear. It's 180 degrees. We can do it under different perspectives, right? From the bottom up, from the side, from the top, from the front. You can look at XCF4. I think that's another one that we did. So this is the octahedral. So notice the bond angle is 90 degrees all the way around. 2 lone pairs. We're able to look at different perspectives here. And so what else did we look at? CH4. So this is a tetrahedral. Right? Notice that it's 109.5. Any way I turn it, it's 109.5. And you guys can move these atoms too. So if you move the atom, once it reaches equilibrium, it still goes back to 109.5. Okay. So you guys can go ahead and explore this. This is BF3. This is trigonal planar. You know what? So with your molecular model kit doesn't have trigonal planar, but the simulation really does a good job with representing trigonal planar. Trigonal means there's 3 sides, 1, 2, 3. Planar means flat. So if I rotate it in the side perspective, you can kind of see that there's nothing jutting out left or right. Everything is just kind of in plane with a central atom top and bottom. And so hopefully this kind of helps you. So this is ClF3. This is the T shape. So notice how in the T shaped, it's less than 90 degrees. And specifically it's 87.5. We can see the 2 lone pairs that's sticking out. So this is the general shape of the T-shaped. I don't think we did anything else from this list, right? And so hopefully this helps you guys visualize the 3-dimensional structure of these molecules. If you guys want to build it from scratch, you guys can click on models. So at the very bottom of this website, it allows you to go between model and real molecules. So if I click on model, how this works, you guys can check off molecular geometry and electron geometry and show bond angles. So when you're building it yourself, you just click on the type of bond. So here is a triple bond, and then everything kind of pops up linear, linear. So you can do another single bond. And then once you have that, you have the bond angle, which is 180. If you click on X, it removes that bond. You can add in a lone pair, for instance, right? And so you guys can go ahead and explore different shapes. So I'll just go through single bonds. So this is linear. This is trigonal planar. So notice how the bond angle starts decreasing. If I have 4 bonds, it's no longer 120, it's 109.5. If I add another bond, that's 90 degrees, right? But, so for trigonal bipyramidal, it's 90, 90, 90. But then if I go from the top down, notice that it's 120. So anything equatorial is 120, equatorial to axial is going to be 90. If I add in one more bond, I get octahedral, and the bond angle is 90 all the way around. And so you guys can go ahead and add in lone pairs. If you want to explore square pyramidal, if I remove this and add in 2 lone pairs, oops, I need to take out 1 bond, add another lone pair, I get square planar, right? If I take out 1 bond and then add another lone pair, I get T-shaped. And so this tool will probably be handy for Chem100 for those who are moving forward. So just go ahead and keep this in the back of your pocket. Let me see here. Any questions? Right. And so once again, when you guys are submitting your last lab, scroll all the way down. It says Lewis structure worksheet upload. You guys can upload as many documents as you need. And so if you're having a hard time merging the pictures with all of the writings that we did, you guys can upload 2 separate documents. One Word document is just all the pictures of all the molecules. Make sure to identify what I'm looking at. And the other document can be the other stuff that we wrote in, like the Lewis dot structures and all that stuff. So this lab is due next Friday. So we only have 1 week left, and next week is finals week. Isn't it crazy? We're like 2 weeks from Christmas. Is anybody done Christmas shopping? Anybody do Christmas shopping?
As much as my bank account would allow.
Same.
Amen. Lots of candy canes for sure. Or maybe like, I don't know.
$5 gift cards to Starbucks.
That's true.
I've been actually kind of double dipping on that because there's another coffee shop called Better Buzz. So I've been going over there, and it says if you get a gift card for $25, then you can get a free drink. So I've just been buying gift cards and getting my own free drink.
Hey, there you go.
So
That's hopefully you have been knocking out a lot of presents.
yeah.
And so don't be ashamed if you're using some of those gift cards for yourself during finals week.
Oh yeah.
So yeah, today is, so for those who don't have me for lab, your lab professor might actually assign you the gas law lab. I am not doing a gas law lab. I do not understand why Chem100 and Chem110 is adamant in having labs the last week. I am not gonna have you guys do any labs next week. You guys just need to focus on your finals. And so today you guys do have an assignment that's due. So you guys have the titration. So you have 2 things you have to submit: worksheet 4 and your screenshot of your titration level 2 upload, or whatever it's called. So that's due tonight by 11:59 p.m. Next Friday is your Lewis structures. And once I have everybody's grades finalized, for those who are in my lecture, I'm projecting that the 22nd or the 23rd is when I'll have all grades finalized. I can't finalize Chem100 grades until every single lab professor submits the lab scores to me. So for those who have me for lecture, but don't have me for lab, I have to wait for your other lab instructors to send me your lab scores so that I can incorporate it in your final grade. Likewise, if you are not in my lecture, I have to send your lab grade to your lecture professor. And I will do that as soon as the Friday deadline, the 17th is up. So 18, 19, 20, I'm going to be working on final grades and submitting that to your lecture professors if you don't have me for lecture. I don't know when your lecture professors will post your final grade for the course, but for those who have me for lecture, you guys can expect all final grades to be submitted either on the 21st or the 22nd, depending on how fast other lab professors are submitting lab grades. And please remember that lab grades are worth 25% of your overall score. And I actually urge you to look through your grades because if this is a department policy, if you guys are missing more than 3 lab assignments, not counting the one that I'm skipping out on, you guys are going to automatically fail the course regardless of what your grade is for lab or lecture. And so if you are missing more than 3 lab assignments, you will automatically fail both lecture and lab. So if there are any assignments that you missed and it's more than 3, this is the time to email me and ask if you guys can reopen any of the assignments. I'll reopen it. And so you just need to get it down to 3 if you're missing 4. Any questions, comments, concerns?
On the assignment that we're submitting, I did it separately for, it's like 2 separate documents for the pictures.
Mhm.
And I'm so sorry. It did like, so I labeled each one, but it did like not the label and then the picture on separate pages.
Okay, that's fine. I'll find it.
I'm so sorry.
Yeah, no, you're fine. And so it's just formatting stuff. Let's see here. I don't know if you can kind of resize your pictures. And so maybe if you can resize your pictures to a smaller picture, maybe it'll fix whatever needs to be fixed.
I tried.
Oh,
It messed up with the numbering.
It is what it is. So don't worry about it. I just need, you guys do need pictures for your molecular models. Let me see here. So really important, right? So 25% of your final grade, if you guys skip more than 3 lab assignments, you automatically fail the course. It's should be in everybody's syllabus. It's a department policy for all chemistry labs. Let's see here. If you guys are kind of struggling in lecture, that 25% in your lab, when it does get incorporated, you guys should see a slight boost in your grade. By how much, I have no idea. It just really depends on each person's circumstance or individual grades of where they're standing at right now. Let me see here. Can't think of anything else. Christmas Eve is not on a Friday. 25th is, oh man, so 25th is on a Saturday. You know, it'd be really cool to have the 25th like either on a Friday or a Monday. So that way people can get like a longer weekend. Oh, same thing here. New Year's is on a Saturday. Well, I guess that's a good thing. Friday night is New Year's Eve. You guys can go out and party. Let's see. And so I think that's pretty much it for me. I know I'm over time. I want to thank you guys so much for hanging in there, hearing me talk for 3 hours every single Friday. I know it's a lot. And so big ups on you guys for sticking with me throughout the semester. I'm running out of steam. I wish I can express more excitement, but my throat is dry. What else? If I don't see you guys for any other chemistry courses, I wish you guys luck in future endeavors. Hopefully our paths cross fall 2022. I don't know what my schedule is like for the fall of 2022, but there is a chance that I might teach 115 in fall 2022. So next semester, I'm just teaching 104 and 100. Actually 100 labs specifically. Any questions, comments, concerns?
Nope.
Not related
right,
to
guys.
chem.
I'm sorry.
Nothing related to chem.
Nothing related to chem. All right, and so I'll go ahead and stop my recording.